So there are two basic definitions for absolute value. One is a geometric definition of absolute value. You guys can all see the screen, right?
Yes.
Yes, okay. So you probably learned this sometime a long time ago when you were talking about absolute value. Somebody was like, oh, here's a number line and there's 0 and here's 5. What's the absolute value of 5? Well, it's just 5, right? And then somebody was like, yeah, that's the distance on the number line from 0 to 5. It's the distance from that number you're taking the absolute value of to 0, right? Did somebody ever say that to you?
Sort of.
Sort of. Good. Sort of is better than no. What about the absolute value of -7? That should just be
7.
7, because it's the distance on the number line from 0. So that is generally like when you take, I don't know, whatever class you take when they teach you about absolute value. I think they call that class first grade. They teach you that it's the distance from 0 generally, and they don't go into any more detail about it. But there is an algebraic definition of absolute value that is extremely important to calculus. And it's pretty straightforward, but we do need to at least briefly talk about what it is. So the algebraic definition of absolute value says that if x is greater than or equal to 0, the absolute value of x is just equal to x, right? Which should be true, right? The absolute value of 0 is 0. The absolute value of 5 is just 5. The absolute value of any positive number or 0 is just that positive number or 0. But what happens if x is less than 0? If x is less than 0, the absolute value of x just becomes what?
X times -1.
Right, x times -1, or we'll just say the opposite of x, right? Whereas, you know, the absolute value, like you said, of -7 is the opposite of -7, or it's just 7. Good? Whether anybody ever taught you this or not, I have no idea, because I don't have any faith in any math teacher that you've ever had in your entire life. So I want to make sure you understand that this is the algebraic definition of absolute value. It's very important. If you didn't know that, you need to know that now. Everybody good there with that?
Yes.
Wonderful. All right. So we are going to use that algebraic definition to evaluate each of these. Well, we're going to evaluate the first two limits, and then we'll be able to know what the third one is afterwards. So if we are looking at the limit as x approaches 0 from the left of f of x, that's the limit as x approaches 0 from the left of the absolute value of x over x, right? What does that tell you about every x value when you're doing a one-sided limit approaching 0 from the left? Every x value that you are concerned about must be
Less than 0.
less than 0. And if x is less than 0, what is the absolute value of x?
Just X. Well, like the opposite of.
Right, it's the opposite of x, right? That's our definition, right? And if x is less than 0, what's x? Well, x is just x still, right? And so we could rewrite this without the absolute value as -x over x, and then we can cancel out the x's to just get -1. And in a little while, we're going to talk about limits of constants, right? The limit as you approach any constant, it's just that constant, and you end up with -1. Everybody good with that or no?
Yeah.
Now, what about as we approach 0 from the right? What do you know about all of the x values? All the x values, if you're approaching 0 from the right, ought to be
greater than 0.
They ought to be greater than 0. So now when we do this limit, the limit as x approaches 0 from the right of absolute value of x over x, we ought to get the limit as x approaches 0 from the right of, well, for positive values, absolute value of x is just x. And x is in the denominator, still just x. And what do? Cancel the x's. And the limit of that constant is just that constant. And now based on our definitions from before, if the limit from the left and the limit from the right are not equal to each other, the two-sided limit
Does not exist.
does not exist. Everybody good with that? Cool. So we can clearly see that there are two ways to go about this one, geometrically or graphically, and also algebraically. Let's do another one that's very similar to this really quickly, and then we're going to move forward and look at some piecewise defined functions. So we're going to do the limit as x approaches 7 from the left of the absolute value of x minus 7 over x minus 7. So if x is approaching 7 from the left, what does that tell you about x? X is always
negative.
X is not necessarily always negative.
Less than 7.
X is always less than 7, which tells you that x minus 7 is always less than 0, or always negative. And we are concerned about x minus 7 because that's the thing that's inside the absolute value. So if we have this limit and we know that x minus 7, the thing inside the absolute value, is always negative, when we take its absolute value, we get the opposite of it. And what can we do? Cancel the x minus 7s. And get -1. And you'll notice the limits unit that we're doing here progresses. My handwriting on limit gets worse and worse and worse. Sorry about that. Everybody good there getting -1?
Yep.
Perfect. All right. As we approach 7 from the right, we know that x is always greater than 7, or that x minus 7 is always greater than 0. So this limit just becomes x minus 7 over x minus 7, right? The absolute value disappears because it's just redundant if the thing inside of it is already positive. And now we'll approach 7 from the right of 1, which is 1, and the two-sided limit does not exist. The one-sided limits aren't the same. Good or no?
Good.
Perfect. All right. Here's our next one. We're going to do this piecewise defined function. So what I'd like you to do is take 30 seconds here, a minute maybe, and graph this piecewise function. Right? And then we're going to find each of these limits. So you got like a minute to do that. Ready, go. What did your graph look like? You should have had an open circle here, and 3 minus x would, well, that doesn't look like a line. 3 minus x should have looked something, that looks better. Should have looked something like that. And then at x equals 1, it should have been 4. And then to the right of this, it should have been going up like a parabola. This doesn't look much like a parabola. That looks better. Is that basically what you had for your graph?
Yes.
All right, perfect. And we should have noted then that just doing this, looking at the graph, as we approach 1 from the left, what does it look like we're going towards?
2.
2. And what about as we approach 1 from the right? Looks like we're going towards
2.
2, which means the two-sided limit should be
2.
2.
And remember, we're not concerned about what happens at x equals 1, which is it equals 4. We're only concerned about what happens as we approach x equals 1. Everybody good there? I hope. All right, if I was doing this algebraically, if we talk about 1 from the left, we should be thinking about the x is less than 1 part of this piecewise function. So we should use the 3 minus x, which gives us 2. And if we were thinking about the 1 from the right, we should be thinking about when x is greater than 1, which means we should use x squared plus 1, which also gives us 2. Everybody good with that algebraically also?
Yep.
Perfect. All right. That's the only piecewise one we're going to do. So now we're going to fly through a few rules for limits that you just sort of need to vaguely know about. And we're going to learn how to apply them later on. And we're also going to get into a really cool theorem that's going to give us some fun stuff to deal with. So the first important rule is one I briefly mentioned a little bit earlier, but it's that the limit of a constant is the constant. So the limit as x approaches a of any constant is just that constant. If I asked you what's the limit as x approaches 3 of 7, it's 7. If I asked you what's the limit as x approaches negative 4 of 10, it's 10. If I asked you what's the limit as x approaches pi of, I don't know, 3,000, it ought to be 3,000. Okay. Reason being, these are all just horizontal line functions, right? The y value doesn't change on any of them. No matter what value you approach, you're still right there at that same y value. Everybody good with that or no?
Yeah.
Cool. All right, our next giant here set of limit rules only can work if we have two different functions and the limits as you approach a of both of those functions both exist. And 4 of the 5 of these are very similar. The first is that if you have one function plus another function within the limit, so x squared plus x, you could separate that as 2 separate limits, the limit of x squared plus the limit of x. Or if you had the limit of sine x plus cosine x, you could do the limit of sine x plus the limit of cosine x. You could do the same thing with multiplication. If you have 2 functions multiplied together, for example, sine x times cosine x, I could do the limit of sine x times the limit of cosine x. Same thing with division. The only caveat with the division one is that the denominator one, the one that you put down in the bottom, can't be equal to 0. Otherwise, that doesn't work out. I'm going to skip this one for a second here. You can also separate them using subtraction. Everybody good with all these separation ones where you separate with addition, subtraction, multiplication, and division?
Yes.
All right. Last one then, which pops up fairly often and is really convenient for some things that we're going to do, is that if I have a constant times a function inside of a limit, I can take that constant out and put it in front. And the reason that this is allowed is this other rule right up here. Suppose I have something like the limit as x approaches a of 5x to the 4th. Well, I could write that as the limit as x approaches a of 5 times the limit as x approaches a of x to the 4th. True? According to that multiplication rule, 5x to the 4th is 5 times x to the 4th. Yeah, hopefully. And what is the limit of a constant? It's just the constant. So that constant can just be pulled straight out and thrown in front of the limit. Now, you may not think that that's very significant, especially for some simple, easy function like 5x to the 4th. And it's not not very exciting for something, or there's no reason for us to do this with 5x to the fourth. But when we get into dealing with some trig functions, it's going to be exceptionally important. So we'll want to remember that rule very well, that you can pull a constant out. Everybody good or no?
Good.
All right. Next little set of rules is that if you have a function being raised to a power within a limit, you can pull the power completely outside of the limit and apply it after you evaluate the limit of the function. So the limit as x approaches 2 of 3x plus 4 to the 5th power could be written as the limit as x approaches 2 of 3x plus 4, all raised to the 5th power, which doesn't seem very exciting or worthwhile when you have a simple little function like 3x plus 4 to the 5th power. But I promise you that when we start dealing with trig functions, you're going to be very appreciative of this rule. Good or no?
Just give like 1 minute.
Sure. And while you're finishing writing that down, the reason this rule works out is because really what do we have in here? We have 3x plus 4 times 3x plus 4 times 3x plus 4 5 times, and we can separate using the multiplication rule. So we have the limit as x approaches 2 of 3x plus 4 times the limit as x approaches 2 of 3x plus 4, right, 5 times. And so really it's just like having one of those being raised to the 5th power because we're multiplying it by itself 5 times. Everybody good there now or no?
Yep.
All right. Last little rule here that is a significant and important one is that you can do the same thing with root functions. And you can pull these exponents out of the root functions, and that you can just directly evaluate any function that has a rational exponent on it. So m over n, or any function that is written as the nth root or the nth root to the mth power. You can just directly evaluate those by just plugging in whatever the a value is, and you should, unless it comes out to be indeterminate, just get a good, nice, simple answer. Good or no? All right, so just for fun, why don't you guys really quickly, it shouldn't take you more than like 30 seconds, real quickly, see if you can evaluate that limit. Ready to go. What is 8 to 2/3?
4.
Yeah, it should be 4. I'll write out the rest of it first, right? 8 to the 2/3. Remember that when you have a rational exponent, if you can do the root first and get a clean number, do that. So cube root of 8 is 2, 2 squared is 4. So we end up with 4 minus 2 root 2 times 3, or 6 root 2, over 4 minus 2, which is 2. Divide both the 4 and the 6 root 2 by the 2, and you got 2 minus 3 root 2. Sorry, those are pluses up there, weren't they? I don't know why I wrote a minus the whole way through, but that was a plus. Easy enough? I hope.
Yep.
Cool. All right, now we're going to get to something that's a little bit more conceptual. This is our first real theorem of the year, and it's a fun one. It's going to make you hungry for lunch. It is called the Sandwich Theorem. My 7-year-old is laughing in the background at my hilarious joke that it's going to make you hungry for lunch. The Sandwich Theorem, sometimes called the Squeeze Theorem. So when we talk about this theorem, there is an initial condition that has to be set first. And that is that we have to have 3 different functions, one of which, in this case, I've called it h of x, is sandwiched or squeezed between the other 2 functions. So that for every x value on some open interval that contains some number a, f of x is always less than or equal to h of x, which is always less than or equal to g of x, except maybe at a. And the only reason we say except maybe at a is because it's possible that the value at a for any or all of these functions might not be defined. And so the limit that we're going to be interested in is the limit as x approaches a of h of x, the function that's sandwiched between. So generally the problems will be like, hey, find this limit of this function. And there won't be another good way to do it, except that you'll have to find some function that is always greater than or equal to that one, and some other function that is always less than or equal to that one, that both have the same limit at x equals a. That makes sense? Sort of. And if we can find the limit of the upper function and the limit of the lower function at a, and they're equal, well, then that must mean that the limit of the sandwiched function is also the same as the other 2. Does that conceptually make sense or no? Anybody? Yes, no, maybe? Can you guys still hear me? You just all ignoring me?
Yeah.
Yeah, it makes sense.
Makes sense. I hope it makes sense. Okay. Right. We got one function that's always above our middle function. We got one function that's always below it. If the upper one and the lower one have the same limit at a, then the middle one must also have the same limit. So we're going to start off by looking at the function x squared times the sine of 1 over x squared. And we're going to see if we can use the sandwich theorem to prove that the limit as x approaches 0 of that is 0. So how are we going to get that started? Well, what's the first thing we should always do with a limit? Even though it says sandwich theorem, what's the first thing we should always do with a limit?
Plug in the variable.
Plug it in. So we get 0 times the sine of 1 over 0. Okay, well, 0 times anything is 0, isn't it? So we're done? Didn't need the sandwich theorem? I wish that was true. But this is 0 times the sine of something that is undefined. And the sine of something that's undefined would be something that's undefined. And 0 times something that's undefined is unfortunately not just 0. So that's not going to quite cut it. We're going to have to do something else. Any thoughts on what we should do? Great idea. Let's look at the graph on Desmond. X squared sine 1 over, oh, that's not right, sine of 1 over x squared. Yeah? What's going on? There we go. Isn't it cool? You guys like that graph? It looks cooler when I zoom in a little bit.
It does, yes.
Yeah. So it sure looks like it's having kind of like we did sine of 1 over x the other day, right? It's having an infinite number of these oscillations, but sine of 1 over x, they were all going up to 1 and down to -1 and up to 1 and down to -1, right? Well, here, that doesn't seem to be the case, right? They've already, they've narrowed out and we're already less than 2/10 and then getting smaller and smaller and smaller. looks like they may be approaching 0 down there. But we can't be sure of that just by looking at the graph. We have to find some algebraic way to prove it, which means we got to find some function that's always greater than or equal to this, and some other function that's always less than or equal to this, that both have a limit of 0 at x equals 0. Any thoughts on what those functions might be?
You could do x squared and negative x squared, I think.
X squared and negative x squared, you think? All right, let's try then. There's x squared, looks pretty nice. And there's negative x squared, also looks pretty good, doesn't it? Sure looks like x squared is always above or equal to, because it touches these functions, right? And looks like negative x squared is always less than or equal to our other function, doesn't it? You guys agree?
Yeah.
Well, let's zoom in as far as we possibly can and tell. Well, now it's really hard to tell, right? It certainly looks like those are good functions for this. But we can't be guaranteed of that unless we do some algebraic work to prove that that's true. And I'm going to tell you, you're right. Those are the right functions. But let's prove that they work. So tell me what you know about the sign of 1 over x squared. Just the sign of 1 over x squared. Forget about the x squared for a second.
The range is between -1 and 1.
That's right. It's always less than or equal to 1, greater than or equal to -1. Would you all agree with that? And whenever you take the sine of an angle, doesn't matter what the angle is, doesn't matter if this is 10,000x in here. When I take the sine of it, I always get something out between -1 and 1. Same is true for cosine, right? Yeah. Okay. Well, this inequality already looks very similar to the type of inequality that we want for the sandwich theorem. But instead of having sine of 1 over x squared in the middle, I need to have x squared times sine of 1 over x squared in the middle. So how can I get an x squared in there?
Would you multiply all parts of the inequality by x squared?
Exactly. I'm just going to multiply them all by x squared, which gives me an x squared on the right and a negative x squared on the left, which is exactly what we were looking for, isn't it? We wanted to show that x squared sine of 1 over x squared was always between negative x squared and x squared, and we've done that. So we haven't proved the limit yet, but we've at least found the two functions. Now, we already knew what they were because we looked at it on the graph, but we've proven that those two functions are functions that will complete the initial conditions of the sandwich theorem. Everybody good with that?
Yes.
All right, so all we have to do then is show that the limit as x approaches 0 of this is the same as this. And whatever we get, which should be 0, we hope, should be the limit of the center one, the one that's squeezed between. So what's the limit as x approaches 0 of negative x squared?
0.
And what's the limit as x approaches 0 of x squared?
Also 0.
So 0, and so by the sandwich theorem, we can say that the limit as x approaches 0 of x squared sine 1 over x squared is also equal to 0. Easy enough. Any questions or issues with that?
No.
Okay. Here is another one, very similar. I'm hoping that you can use this same idea of what we just did on this one to successfully solve this next one. Do you think that you can do that? Hopefully so. All right, I'm going to give you guys 2 or 3 minutes to work through that on your own, and then we'll talk about it and make sure you guys did it correctly. So ready to go. All right, so we should have started with the knowledge that cosine of 1 over the cube root of x was always less than or equal to 1 and greater than or equal to -1. Right? And then we can just take each piece of this and multiply it by x to the 4th. And that gives us our function that we want, the limit of, sandwiched between 2 other functions that are very easy to find the limit of. Just find those 2 limits, both of which are 0. And then you can say that by the sandwich theorem, the limit as x approaches 0 of x to the 4th cosine 1 over cube root x is also equal to 0. Good or no?
Yes.
Cool. All right, now I know you're sitting there thinking, this is easy. Why is he going to force us to do a third one of these? Well, I'm going to force you to do a third one of these because this one has a little bit of a problem with it. So we should be able to start this off the same way with the sine of 1 over the cube root of x always being less than or equal to 1, greater than or equal to -1. True?
True.
Okay. But now, what do I need to multiply each piece of that by?
X
X to the
cubed.
third.
Yeah, x to the 3rd, x cubed. And what's the problem with doing that?
The limits are different, right?
Say that again?
Aren't the limits from like the left and right different for
I'm not sure exactly what you mean. Are you talking about the limits at 0? Because the limits at 0 of both x cubed and -x cubed are 0. But there's something happening with x cubed at x equals 0. What happens with x cubed at x equals 0?
I'm confused. Wouldn't it just equal 0?
Sorry, I couldn't hear you. The trash truck was going by my house. What did you say?
Like, I'm not sure, because wouldn't it just equal 0?
Right, the limit just equals 0, but the function itself, right, x cubed, is crossing through the x-axis. It's changing signs, isn't it? X cubed goes from being negative to being positive at x equals 0. Which means that when I multiply by x cubed is sometimes positive, but x cubed is also sometimes negative. True? Would you all agree with that? Sometimes x cubed is positive and sometimes it's negative?
Yeah.
yeah.
Yeah. X squared, right, and x to the 4th from the last 2 problems, right, x to the 4th, that's never negative, right? Not a problem. X squared, never negative, not a problem. But x cubed is. And when you multiply an inequality by something that is negative, what has to happen?
You flip the
Flip
direction.
signs.
Yeah, you have to flip the inequality signs, right? So we have to separate this out. One case of this will be when x is greater than 0, because that makes x cubed positive. And the other case will be when x is less than 0, because that will make x cubed negative. So we will say if x is greater than 0, negative x cubed is less than or equal to x cubed sine of 1 over the cube root of x is less than or equal to x cubed. Everybody agree with that? If x is positive, x cubed is positive, and I can just multiply each piece by x cubed without changing a thing.
Yes.
But if x is less than 0, then when I multiply by that x cubed, I get negative x cubed still, but I should get greater than or equal to x cubed sine 1 over cube root x. And I should get greater than or equal to x cubed. Everybody agree and okay with that?
Yeah.
All right.
Can you leave
So,
that up for just a few more seconds?
Yeah, I can wait a second. Good to move on now?
Yeah, that's fine.
Okay. All right, so over here, what do we want to find? We want to find the limit as x approaches 0 of negative x cubed and x cubed, right? But what's the problem with finding the limit as x approaches 0 of those? X is only positive. So can I find the limit as x approaches 0 if I only have positive x values?
Wouldn't you have to only do like the right side?
I can only do the right side because I'm only looking at positive x values. I can't approach 0 from both sides. I can only approach from the right, which doesn't make the limit any more difficult per se, but what's the limit as x approaches 0 from the right of negative x cubed? Well, it's 0. And that ought to be the limit as x approaches 0 from the right of x cubed also. Right? Both of these have to be limits from the right because x is greater than 0. And if the limit from the right and the limit from the left, the limit from the rights of both of the lower and upper functions are both 0, then by the squeeze theorem, the limit as x approaches 0 from the right of x cubed sine of 1 over cube root of x is also equal to 0. Everybody okay with that? And what about over here? For this one, I'm going to have to do a limit from the
left.
because x is less than 0. And that doesn't make the limit any more difficult. It's still 0, right? For both negative x cubed and positive x cubed. And since both of those limits on the outer functions are 0, the one that is squeezed between them is also 0. And from there, now that we know that the limit from the right of this function is 0 and the limit from the left of this function is 0, if and only if that's true, should the two-sided limit also equal 0. And that is our full proof of why that limit is 0. So we got to be a little bit careful about what we're multiplying by. If we're multiplying by something that could be negative, we have to split the domain of it up into different pieces and work each part separately. Everybody good with that or no?